Geometric correspondence and verification. Welcome, everyone. Before we dive into today's new material, let's take a moment to recap what we've already covered. In our previous lessons, we established the fundamental concept of similarity, the idea that two figures are similar if they possess the exact same shape, even if they aren't the same size. Now, while it might be easy to look at two shapes and say, hey, those look alike, in mathematics, we can't simply rely on our visual intuition or a gut feeling to make a claim. To move from a guess to a mathematical proof, we need something much more rigorous. We need a systematic, organized way to match the specific parts of one polygon to the specific parts of another. This precise process of pairing up vertices, sides, and angles is what we call establishing geometric correspondence. Over the next few slides, I'm going to show you exactly how we identify these partners and how we use them to verify similarity with absolute certainty. Understanding correspondence through magnification. Now that we've established that similarity is about shape rather than size, you might be wondering how we actually match parts of one shape to another. To make this concept of correspondence more concrete, let's look at a practical, real-world example: the way a light source creates a shadow. To make this concept of correspondence more concrete, let's look at a practical, real-world example: the way a light source creates a shadow. Imagine you have a small cardboard cutout of a polygon, and we will label its vertices as polygon A, B, C, and D. Now, place this cutout in front of a single point light source. As the light passes through the edges of your cutout, it projects a much larger version of that same shape onto a wall behind it. We can call this larger shadow polygon A', B', C', and D'. Even though the shadow is much bigger than our original cardboard piece, the shape remains the same because it is simply a magnified version of the original. In this scenario, every single point on your original cardboard cutout has a specific partner or a corresponding point on the shadow. This idea of partners is exactly what we mean when we talk about geometric correspondence, which we will define more precisely in the next slide. How to identify corresponding vertices. Imagine you are looking at that same setup: the light source, the cutout, and the shadow on the wall. If you were to take a ruler and draw a perfectly straight line starting from the light source, passing directly through vertex A of your original cutout, you would see that this line continues on and hits the wall at the exact same spot as vertex A' of the shadow. This isn't a coincidence. It's the foundation of how we link these two shapes. Following this same logic, we can see a clear pattern for the rest of the shape. Vertex A corresponds to vertex A', vertex B corresponds to vertex B', vertex C corresponds to vertex C', and finally, vertex D corresponds to vertex D'. Now that we have the concept of magnification in mind from the previous slide, let's look closer at how we actually identify which parts match up. As we move to the next slide, we will see the specific mathematical symbol we use to write out these pairings. Symbolic representation. Now that we have visualized how the light source connects the original shape to its shadow, we need a way to write this down formally. In mathematics, we don't just use words to describe these connections, we use a specific shorthand. To represent this relationship of correspondence, we use the double-headed arrow symbol, which we pronounce as corresponds to. So, looking at our example from the previous slide, we can write this out clearly. A corresponds to a prime, B corresponds to B', C corresponds to C', and D corresponds to D'. Using this notation allows us to precisely define which parts of our first polygon match up with the parts of our second polygon before we move on to the actual mathematical verification. Mathematical verification of similarity. Now that we have established how to pair up our vertices using that double-headed arrow notation, we move on to the most critical part of our lesson, the mathematical verification. It is not enough to simply say two shapes look alike, we must prove it. To determine if two polygons are truly similar, we must satisfy two simultaneous conditions. This means you cannot just check one and stop. You must verify both requirements, and they must both hold true at the same time. If even a single part of our check fails, if just one angle is off or one side ratio is inconsistent, then we must conclude that the two figures are not similar. Condition I: equality of corresponding angles. Now that we have established how to identify which parts of our figures match up, let's move on to the first of our two essential requirements for similarity. The first step in our verification process is to ensure that the shape itself has not been distorted or stretched unevenly. To do this, we must verify that all pairs of corresponding angles are exactly equal. Looking at our polygons, A, B, C, D, and A', B', C', D', we need to check four specific equalities. Angle A must equal angle A', angle B must equal angle B', angle C must equal angle C', and finally, angle D must equal angle D'. If even one of these angles doesn't match, we cannot proceed, as the shape's fundamental structure has been altered. Condition II: proportionality of corresponding sides. Now that we have verified that the angles are identical, we move on to the second and final condition for similarity. The second step is to ensure that the figure has been scaled uniformly. Think back to our shadow analogy from earlier. When the light projects a larger version of the shape, it doesn't just stretch the shape vertically or horizontally, it expands it evenly in all directions. This means that the ratio of every pair of corresponding sides must be exactly the same. To check this mathematically, we calculate the ratios of the sides as follows. The length of side AB divided by the length of side A'B' must equal the length of side BC divided by side B'C', which in turn must equal the length of side CD divided by side C'D', and finally, the length of side DA divided by side D'A'. If this constant ratio exists across all four sides, then we say the sides are in proportion. Once we have confirmed both this proportionality and the equality of angles we discussed in the previous slide, we will be ready to move into a practical, step-by-step example to see this verification in action. Step-by-step example: verifying similarity. Now that we understand the theory behind correspondence and the two conditions required for similarity, let's put this into practice with a concrete example. Suppose we are presented with two quadrilaterals named A, B, C, D, and P, Q, R, S. To begin our verification, we are given a specific rule for how these shapes relate to one another, known as the correspondence. In this case, we are told that vertex A corresponds to vertex P, vertex B corresponds to vertex Q, vertex C corresponds to vertex R, and vertex D corresponds to vertex S. Our very first step in the verification process is to systematically list all the corresponding parts, so we don't miss anything. First, we identify the pairs of angles that must be checked for equality. These pairs are angle A with angle P, angle B with angle Q, angle C with angle R, and angle D with angle S. Next, we must list the pairs of corresponding sides that we will need to check for proportionality. These pairs are side AB with side PQ, side BC with side QR, side CD with side RS, and side DA with side SB. By laying everything out clearly like this, we set ourselves up for the next two steps, which we will cover in the following slides: verifying the angles and then calculating the side ratios. Step-by-step example: verifying similarity continued. Now that we have listed all our corresponding parts in step 1, we move on to step 2, which is to verify the angles. Remember, as we discussed earlier in the lesson, we cannot rely on just looking at the shapes. We must mathematically confirm that the shape hasn't been distorted. To do this, we check if each pair of corresponding angles is exactly equal. Specifically, we need to check if angle A equals angle P, angle B equals angle Q, angle C equals angle R, and angle D equals angle S. It is vital to be thorough here. If even one of these angle pairs does not match, the condition for similarity fails immediately. However, if all these equalities hold true, then we have passed the first hurdle. and we can proceed to the next step to check the side ratios. Step-by-step example, verifying similarity continued. Now that we have successfully verified that all the corresponding angles are equal, we move on to the third and most critical step in our verification process. Step 3, which is to calculate the side ratios. Remember, as we discussed in the previous slides, having equal angles is not enough to prove similarity. We must also ensure the figure has been scaled uniformly. To do this, we need to find the numerical value of each fraction by dividing the length of a side from our first quadrilateral by its corresponding side from the second quadrilateral. Specifically, you will perform 4 separate calculations. First, find the ratio of side AB to side PQ. Second, find the ratio of side BC to side QR. Third, find the ratio of side CD to side RS. And finally, find the ratio of side DA to side SB. As you perform these divisions, keep a close eye on your results. In the next slide, we will see how these individual values lead us to our final conclusion regarding whether or not these two shapes are truly similar. Step-by-step example, verifying similarity conclusion. Now that we have calculated all our individual ratios in the previous step, we reach step 4, our final conclusion. This is the moment of truth where we bring everything together. Look closely at your results. If the ratio of side AB over PQ is exactly equal to the ratio of BC over QR, and also equals the ratio of CD over RS, and finally matches the ratio of DA over SB, then you have successfully proven your case. When all these ratios are identical, we can state with mathematical certainty that the two quadrilaterals are mathematically similar. However, remember, if even one of these fractions differs from the others, the similarity fails. Once you've made this determination, we will wrap up our lesson by reviewing the key takeaways and some common pitfalls to watch out for in your exams. Key takeaways. First, let's revisit the concept of correspondence. Remember, we cannot simply look at two shapes and guess if they are similar. Correspondence is the formal, systematic process of matching each vertex of one polygon to its specific partner in another polygon. Next, let's look at the notation we use to communicate this. In mathematics, we use a specific symbol to show this relationship. When you see the notation, capital A with a double-headed arrow pointing to capital A', it is a clear, mathematical way of stating that vertex A corresponds to vertex A'. This shorthand is essential for the step-by-step verification process we practiced earlier. Third, and perhaps most importantly, let's review our verification criteria. As we discussed when looking at the two conditions for similarity, you cannot stop halfway. Similarity is only confirmed when both conditions are met simultaneously. You must prove that all corresponding angles are equal, and you must prove that all corresponding sides are proportional. If even one of these conditions fails, the figures are not similar. Finally, I want to emphasize that order matters. When you are given the names of two polygons, the order in which those vertices are listed is not random. It is the blueprint for your entire calculation. The sequence of the letters tells you exactly which angles to compare and which sides to divide. All right, class, we have covered a lot of ground today, so let's take a moment to recap the key takeaways from this lesson on geometric correspondence and verification. As we move into our next topic, keep these fundamental rules in mind, as they are the foundation for everything we will do with similar figures moving forward. Common mistakes to avoid. Now, as we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of similarity, it is very easy to make small errors that lead to the wrong conclusion. Let's look at 3 specific mistakes to avoid. First, watch out for incorrect pairing. It might be tempting to just look at the two shapes and pair the shortest side of one with the shortest side of the other. However, you cannot simply pair sides randomly. You must always strictly follow the established vertex correspondence that we discussed earlier in the lesson. If the problem states that vertex A corresponds to vertex P, then side AB must be paired with side PQ. Second, be careful not to fall into the trap of checking only one condition. I often see students check that the angles are equal and immediately conclude that the shapes are similar. But remember our two-step verification process. Equal angles alone are not enough. A classic example is comparing a square to a rectangle. They both have 4 90-degree angles, but they are clearly not the same shape because their sides aren't proportional. You must verify both the angles and the sides. Finally, avoid inconsistent ratios. When you are calculating your fractions to check for proportionality, you must be consistent. If you start by placing the side from the first polygon in the numerator and the side from the second polygon in the denominator, for example, side ob over side a prime b prime, you must maintain that exact same order for every single side you calculate. If you accidentally flip one and calculate side b prime c prime over side bc, your ratios won't match, and you'll end up with an incorrect result. Keep these 3 points in mind, and you will be able to verify geometric similarity with much greater accuracy.